So a ball is thrown straight up from a height of 5 feet. Straight up. It goes straight up, falls down, and hits the ground. Draw a qualitatively accurate graph of the height versus time. So time is your input, height is your output. Now what we're imagining here, I'm going to imagine somebody's standing right here with a ball. Okay, and that ball, they just took it and threw it. And the instant they throw it, it's right here. That's its height. And I said no numbers, but it's 5, right? Because it says it's 5 feet. And what happens is it goes straight up, like this, right? And it starts to slow down a little bit. Slow down a little bit. It stops in midair, and then starts coming back down, right? And that's what's going on. And it keeps going down, and it hits the ground. And so what we're imagining here is like, I'm taking every so often, I'm taking a snapshot of what's going on. And as the seconds tick by, I'm keeping track of the height, just simply the height of the ball. And what that would look like is, okay, well, after, say, a quarter of a second, it's right here. After another quarter of a second, it's right here. After another quarter of a second, it's right here. It's where it stops. And then it comes back down. And what you would have would be a parabola, just like this. So it's not that the ball actually moved in this direction, right? All we're doing is we're just tracking one variable, which is the height, right? We're just looking at the height of the ball. And that's the kind of picture that we end up with, right? Yes. Everybody got that? Everybody remembers that from last year. There's nothing new here going on. Okay, all right. What does that have to do with trig, right? Okay,
well,
so.
The ball's a circle.
The ball's a circle, and so there's probably some kind of angle. Okay, homework's right here, right? Don't wait to do these. It's quite a lot. It's more than 10. It's like 15 questions, I think. So, might be 16. I'm not sure. So, okay, today we are going to do, again, as promised, the unit circle. Okay, why do we call it the unit circle? It's because it's what is what?
Its radius is 1.
There you go. Its radius is 1. Okay? Now, in your book, so oftentimes what I'll do is when I draw this guy, I'll put like a 1 here, and a 1 here, and a -1 there, and a -1 there. Your book will do this. It'll have a big capital U by it, so that you know all of that information. The radius is 1, it's centered in the middle, and so that's a 1, that's a 1, that's a -1, and that's a -1. But all your book is going to have is a little capital U right there. And I kind of like that. I think that's kind of slick, right? You don't have to write a bunch of numbers, you just write a U, and we're all on the same page. Now, pick any point on the unit circle. Okay, so I'm going to do that right now. There's my point. We're going to call it XY. This is all review, we've done this before, but I want to go through it one more time, right? Okay, so any point on that circle, what we could do is say, well, its radius is 1, right? So that length right from there to there is 1, and you notice that if you drop a line straight down like that, you make a right angle. And then this right here, this angle, let's call it theta. Now notice I said for any place, and I guess for right now we could say you pick any point in the first quadrant here, and what you'll end up with is a right triangle. And its radius, or its hypotenuse, is equal to 1, just by definition of the unit circle, right?
Yeah.
Right? Okay. And so this is some angle theta. And since this point is x comma y, then that length is what? X. It might be 1/2, it might be 0.702, who knows, right? This length would then be what? Y. And so, okay, what is sine theta?
Y over R.
Y over
Y
which is
Y.
just plain old y, right? And then what's cosine theta?
X.
Right? Because by the way we've done it up until now, cosine is adjacent over hypotenuse, which would be x over 1. But over 1, we don't even need to write it. We could just say that. And so now, it looks like, holy moly, every point can be written as cosine theta, sine theta. Everybody remember that?
Yeah.
Okay? Okay, this is how we will now define sine and cosine. And therefore all of the others too, right? Because every other one can be written in terms of sine and cosine, right? Tangent is just sine divided by cosine. And all the other ones are just 1 over each of those. So right now, this is how we are going to define sine and cosine. Officially, now, in our class, this is how we're going to do it. Watch this. For all t in the reals. In other words, for every real number t, okay, it could be a billion. It could be a billion to the billionth. It could be 0.01. It could be negative pi. Doesn't matter. Any real number. For every, this means for all, and so for all real values of t, interpret t. In radians as the measure of an angle. Okay, so if t was like 1.7, you could say, okay, well then 1.7 radians would be whatever, however many radians I go along before I get to that, you know, whatever. If it's a billion, well, you have to wrap around a few times, but you'll get there, you'll get, that's some angle measure, right? Okay, then, once you've done that, okay, then there is, how did I want to state this? There is a point, x comma y, on the unit circle. I'm just going to do capital U, on the unit circle, which intersects. That's not how you spell which. Is that how you spell which? Which.
Yeah.
Intersects. And this is going back to what we did last time. The terminal side of the angle. So let's draw a picture so we can all make sure we're on the same page of what I've just written right there. Okay, we have this. What we're going to do is this. You give me any number t, and we'll pretend for now that t is positive. And maybe it's really, really big, right? But what I could do is I could take t and just keep wrapping around until I get to whatever the radian measure is, right? And let's say that's where it ends, is right here. Doesn't need to be there, it could be anywhere, but we'll just say it's right there. So then this would be the radian measure of t right there. Well, that's the terminal side of the angle. And therefore, it doesn't matter how big or how small you draw this line. Well, I guess it would have to be somewhat big. But that line right there, which we can imagine goes off into infinity, intersects the unit circle at exactly one place. Does everybody believe that? How could it be otherwise, right? So I'm not saying any, like, I just want to make sure that we're all on the same page. And so where that intersects, we will call that point xy. Okay? So I haven't done any magic. I've just said this, right? Take any real number, interpret it as an angle, then that angle, if you think about a ray going out from the origin, it will intersect the unit circle at exactly one place. Okay? Define. Cosine of that angle as the x-coordinate. Define sine of that, it doesn't really need to be an angle, it's a real number that we're interpreting as an angle, but it's just a real number. That sine of that real number will be the height. And in so doing, we get all of this. Everything that we've already done still applies. There's nothing new here. If your t is this guy right here, then it happens to be that it's that over that. Right? If it's bigger, if your triangle is bigger, we'll just scale it down, and we've seen like 10 times now that it's going to be the same as if you just scaled it down and put it on the unit circle. And so everything we've done up until now, there's nothing new here. This is just how we are officially going to define sine and cosine for the rest of this class. Sine is no longer opposite over adjacent, although you might want to use that from time to time, but that's not how we're going to define it. Okay? We're defining it this way, that they're just simply the coordinates of the unit circle for any given angle. Could have been a negative number, right? I could have said like negative 3 pi, and I've gone that way, 1, 2, 3 pi, and we'd end up right there, and so on and so forth.
So if you just like plug in sine of a number to a calculator, or we use the unit circle, basically.
There's when you take calculus, there's another way that it does this. It doesn't use the unit circle, but this is like, it's all equivalent, right? It would, if, you know, it doesn't like take a measure of something and then go in and find the heights and the widths and then divide them and all that kind of stuff. It does something else that you need calculus for. But it's all equivalent. This is how we're going to use it in this class right here. And that's going to get us beyond simple acute triangles. As you can see, this angle is obtuse, right? We could also do negative angles and stuff like that, and you don't really need to think about them as angles anymore. If we don't want to, we could just think about any real number that you throw in here, it has some output. Any real number that you throw in there, it has some output. Okay, any more questions? Okay, one thing I want to say, there's nothing special about this being t. Like I said, for all t, now you might be thinking, oh, now we're moving out of thetas. No. We're going to be using theta. In fact, oftentimes, I'm only using t right now because when you're in this section in the book, that's what it uses in all your homework problems. It uses t as the angle, and so that's cool, or as the input. We will use theta, we will use x. There's nothing special about any of those as being inputs to these trig functions. Everybody cool with that? We're gonna and might use them interchangeably and whatever. So, okay, given that, so for right now, right, this is, from now on, this is how we're going to think about sine and cosine. This is what they are. They're points on the unit circle. And everything then thereafter just follows from that. Tangent is still sine divided by cosine. So in this case, it would just be the y value divided by the x value. All the others are just, so then cosecant would be 1 over the y value, and so on and so forth. So number 4 from your homework gives you a picture that looks like this. I'm going to draw the picture the way that it does in the book. Okay, it has a capital U, so you know this is the unit circle. It does this, and gives you a point right here. And it gives you that. There's a little arrow so you know which direction it's measured, but it should be obvious. Gives you a T right there. And then it gives you the point. This point, right here. It gives you the coordinates of that point. So negative 5/13. Should the next one be positive or negative?
Negative.
Should be negative, right? Because we're talking about the y value. It's below the x-axis, so it should be negative. And it's 12/13. And if you're so inclined, you can use the Pythagorean theorem to find that if you square that and add it to that squared, you do indeed get big fat 1, which is nice. But we don't need to do that. What it tells you to do, it says find sine t, cosine t, tan t. It just says find the values of the 6 trig functions, right? And it says, I think the way it says it is the trig functions of t or whatever. This is what it means, right? You plug in that value of t and see what you get. So you tell me, what is sine t?
Negative 5/13.
Negative 12/13. By definition now, this is how we're doing it, right? Now, it's still true that if you do this, and you think about the reference angle right there, and don't lose that. That's going to be very helpful for us later on. And we could say, well, that would be whatever that length is over 1. That length is that right there, 12/13, and it's negative, so it's negative 12/13, and so on. What about cosine?
Negative 5.
What about tangent?
You have to multiply negative 12/13 divided by negative.
There you go, negative 12/13 divided by, right? Because it's y over x, or sine over cosine. And so what does that work out to be?
Flip the 5/13 and you get 13 squared over 13 times 5.
13.
Wait, no,
no.
12 times 13.
There you go. And is it positive or negative?
Positive.
Positive. 12 over 5. There we go.
6. Oh, 12 over. So.
Yeah.
And now we have that right.
Okay, now what about cotangent?
5 to 5.
What about this guy?
It's negative 13 over 5.
There you go. It stays negative, right? And you'll notice that this sign is always the same as that sign. This sign is always the same as that sign. And finally, that sign's always the same. That's negative. And so what is that one?
13 over 2.
13/12. There we go. Okay. So that's number 4. Okay. All right. All right. Here we go. This is going to be kind of cool. Any questions with that before we go on?
No.
It's basically the same thing we had been doing, right? It's just now we're on the unit circle, and we're officially, now we've called sine and cosine simply the coordinates on the unit circle. After you've wrapped around however many times and blah, 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 blah. Okay, this is where it's going to get fun. Let's look at number 6. Actually, it'll get fun in a few more minutes. This is 6 is kind of boring. Number 6. Let. And okay, I'm writing this out because this seems just the way that the book words it is kind of. Let P of t be a point.
Is PT a function? Or
Yes. Yes. It's a point. I mean, it's a point and it's dependent on t. Yeah, but it's just the point, right? And that's why I'm writing this out, just so that when you read this and it says that, you're not like, wait, what? What? I don't know what that function is. It's just the point. Let this thing be a point on U. And it doesn't say this, but it's corresponding to, this corresponds to the radian measure T. That's kind of what's wrapped up in here, right? They don't say it, but it's like we're going to interpret T as the just like we did with the previous picture, right? It's just the radians that we're plugging into these functions, okay? Now, here we go. Number 6, so it says some more stuff up at the top above, like 5 through whatever it is. But then, number 6 says, if P of t has the coordinates negative 8 over 17, comma, 15 over 17, and you could check if you want, that certainly is on the unit circle. But anyway, if this has that, if P of t has these coordinates, then find the following. P of t plus pi, P of t minus pi, C. P of negative t, and D is P of minus t minus pi. Okay, what? So, let's draw a picture. That's going to make life so much easier. And in fact, like all the time in this class, drawing pictures is going to help you every single time. So, okay. P of t, so in other words, the angle t, right? We can think about it as an angle being measured from here. And it has these coordinates. So what quadrant is that in?
Second.
Second quadrant. So I'm not going to try to do this like well. I'm just going to do this. There's the coordinates, right? And why don't we go ahead and write them? So minus 8, 17, 15, 17. And so this right here, that is, this angle right there is t. So now what this says is, what would it be if you went to t and then you kept going, adding on another pi radians? Where would you end up?
You end up just halfway across from where we are now.
Yeah, right? Like, in other words, right, like, here's t, and maybe t was actually like a couple 100,000, and so you had to wrap around however many times until t finally terminated, boom, right there. Well, if you kept going another pi radians, you would end up, well, it would be a straight line, wouldn't it?
Points are the same but four.
And yeah, and so what would the coordinates be in that case?
8 17ths and negative 15ths.
There you go, 8 17ths and negative 15 17ths. That's all it's asking. That's the answer to number A. That's where you would be. Okay, what about this one?
Exactly the same.
Exactly the same, because if you go that and then you go back, well, there's something special about pi in a circle, right? Pi is like the halfway, right? So you just go halfway around the circle and you're right back to there. So both of these are 8 17ths minus 15 17ths. For that's the answer to both of those. Okay? Now, here's the fun one. Okay, I'm going to get this out of the way so we don't...
Well, isn't minus t the same? Oh, wait.
Yeah, but it's
Yeah. So let's do it this way. This is how I want to think about it. So, okay. As we, like, if I were to just measure t, I would go, am I at t yet? Nope. Am I at t yet? Nope. Am I at t yet? Nope, 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 nope. Now I'm at t. And so, if I'm going in the opposite direction, that's all that means. It's the same number of degrees or number of radians. You're just going in the opposite direction. And so, when this goes up by that much, that one goes down by that much. When this goes up by this much, that one goes down by that much. When this goes up that much, this one goes down by that much. And then when this one goes over that much, that one goes over exactly that much.
So what is that?
Well, you tell me.
Oh, it'd be.
It's the reference angle. Wait, no, it's not.
Nope.
It has the same points, but they're arranged differently.
Yeah, and so negative t, you tell me, which one of them is the same?
It'd be 15 over 7 is the x. No. Negative 8 over 17 is the x.
Negative 8 over 17
And it's
has not changed.
negative
Did both of you guys get that?
Yeah.
The x value hasn't changed. And you can see that, like, as you start to go, you can just ask yourself, let's go up 1 degree. Okay, then you go down 1 degree. Is the x the same?
Yeah.
Yeah, the only difference is the y, right? As a matter of fact, it looks like the y is exactly the opposite, no matter how much you're going. And even if this wraps around a couple times, eventually it stops, and they're always in that relationship with each other. Now,
Negative 15.
negative 15 over 17. So that's the answer to this guy. Negative 8 over 17, negative 15 over 17. Everybody get that? What that one's asking you to do? And each one of these is the same for each one of these. Or each problem like this. It just gives you a different coordinates. And then you just have to do this type of thing. Finally, minus t minus pi. Well, we already know where minus t is. So if I keep going in that direction, another pi, where do I end up?
Just
Exactly on the other side.
the other side of
In which quadrant? I just want to make sure we're... The first quadrant, right, yeah. In other words, it's a straight line, right?
Yeah.
You add pi or subtract pi from any measure, any radian measure, and you've just now gone to, like, you've made a straight line through the thing, right? And so what would that be then?
Would be positive 8 over 17.
There you go.
Positive 15 over 17.
Right? Let's see. Is that right? Yes. Yes, that's right. 8, 17.
It would be positive 15, right?
Yeah.
That's first quadrant.
Right?
It looks-
That's what I wrote, right?
Yeah, never mind.
Okay, making sure. Okay, so that's 6. And you have a couple like that. Now, check this out. This is where we've just discovered something interesting. In order to talk about it, I want to draw something a bit more general. I don't want to use an exact point. I want to do this. So, can I erase all this stuff? Everybody got all this? This is what these problems are. It's what it's telling you to do. It's worded a little weird. Now check out what we've just discovered. If you're on the unit circle, okay, and you have any input, say that guy right there, here's your theta, right? So you have any angle that you put in, and it goes up however much, and you're here at the point x comma y. What did we just say? What's cosine theta in this case for this guy?
The X.
It's simply x, right? And sine theta is simply what?
Y.
Y. Just by definition. Just simply by definition. That is what we're going to define as cosine theta, sine theta. Okay. And what we've just found is, well, if instead of going up by that amount, if you went down and we measured the negative angle, what we would end up with, so in other words, negative theta right there, would put me at what point?
X negative Y.
X negative y. Everybody got that? Because if that were 1/2, if the height were 1/2 right here, it would be, if you went the opposite direction, you'd be exactly at negative 1/2. If the width here, where it intersects the x-axis, if this point were, say, 0.8, then if you went in the opposite direction, you'd still be at 0.8. Right? And so if cosine theta is 0.8, then cosine negative theta is exactly the same thing. Right? And what did we just say? That sine negative theta would be what?
Negative. Oh, no.
In this case, if the output was y, then it would end up being what?
Negative Y.
And you know, this works no matter how big or how small you draw theta, right? If theta happened to be, and I'll go ahead and do this. Why not? Why not? A little bit of time here. Okay, so if theta ended up being this big, and so I wrapped around past pi radians and ended up all the way over there, and I called this point xy, and you'd say, but wait, x is a negative number and y is a negative. That's fine. That's okay. Like, x can be a negative number. X can equal negative 0.02. That's fine. That could happen, right? They were just saying, whatever those numbers happen to be, yes, x and y both happen to be negative. Right. But now, check this out. If I went in the opposite direction, instead of going this direction, I get to 180 and then move down by that much, I would just do the opposite thing for negative theta, right? I would go all the way to 180 and then up by that same amount, and I'd end up in that direction. And so I've measured it in the opposite direction. Here, like that. There's negative theta. Sorry that looks so terrible. But you see what I did, right? Yeah. If theta went past and ended up there, maybe it wrapped around 17 times and finally terminated right there. That's cool. You do the same thing here, and that'll finally terminate right there. Well, is the x value the same? Yeah, it's still the same x value. There's one right on top of the other. But what about the y value?
It's positive.
It's positive, but that's obviously negative. So how do you make a negative number positive? Make it negative, and so it's negative y, right? Yeah, it's weird. But you get my point, right? Yeah. That no matter where cosine and sine end up, if you plug in the negative of the same input, that will end up at the same place. This one will end up the negative. It'll just get flipped up and down. Everybody get that?
Yeah.
So in other words, another way of writing this is to say that since cosine theta equals x, and that's the exact same thing, cosine theta equals cosine negative theta. What about this guy? In fact, I don't want to write it that way. It's funny how I did that. I want to say this. I want to do it this way. Negative theta is equal to cosine theta. So then sine negative theta is equal to what?
Negative sine theta.
Negative sine theta, right? Because if that's y, negative whatever y is, what was y? Well, we just said y was sine. So it's negative sine theta, so it's negative sine theta. In fact, these functions have this property that in this case, you plug in a negative and you get what it was when it was positive. This function has a property that when you plug in a negative, it becomes negative of whatever the positive is.
This looks familiar.
This does look familiar. This type of function is called a what function? Do you remember?
No.
We didn't quiz on this. I didn't test you on this, but I did bring it up last year. This is called even. Good, even. This is an even function. So therefore, cosine is an even function. This type of function is called a what? Odd. Odd, and therefore sine is an odd function. And what was the thing about symmetry in even functions? Even functions have symmetry about what?
A line. Right? Or is it, yeah, a line.
It's symmetric with respect to the y-axis, which we haven't introduced yet, but we will. Like, it's, if you know this half of it, right? If I know that f is even, and it does this, then I know that it's reflected about this way. That looks terrible, but you get the idea, right? It's like a reflection, it's symmetric that way. Why? Because this says if you go to x and plug it in, you get some output f of x, right? Obviously, this is just what f of x is. But this says that if you go the same distance in this direction down to negative x and plug it in, f of negative x, you get the same height, which is not right here, and I'm sorry. But, right? That's why it ends up being a mirror image across, or with respect to the y-axis. On the other hand, an odd function, it's symmetric with respect to what?
The origin. Right.
Yes.
Or is it, no.
Yeah, no, that's right. With respect to the origin. So, for instance, if my g of x did, something like that, then think about what this says. Here you go to x, you plug it in, and you get out a g of x, whatever that is. That's your height. Well then, if you go in the opposite direction to negative x, this says that you get the negative of whatever that height is. So it would be flipped down to here. And ditto for all the other points, right? This would be negative g of x right here. And it would look something like that, right? You could do that for every one of those. You go over that much, it tells you to go up that much. You do it there, it tells you to go the opposite direction. You go over that much, it goes up that much. You go over that far, it tells you to go in the opposite direction. That's all that means. But this is what it looks like. So, just a quick refresher, and we'll come back to that in just a minute. But this right here, so this is all stuff that we'll see again. But check this out. Okay, so now we know that cosine is even. And this is what it means, right? So like you're going to have identities that you're going to have to do something with. And like you'll probably want to use this fact right here. You'll probably want to use this fact right here. What about tangent? In other words, what's tan of negative theta?
Well, it's
It's
sine over
x.
cos.
There you, let's start there. Let's just start there. We know that tangent of stuff is just sine of stuff over cosine of stuff. And if that stuff happens to be a negative theta, then what do we have up on the board? How could I flip those guys around? Or what do I do?
Negative.
That's
Well, that equals negative y,
Yeah.
right?
Or negative sine of theta.
There you go.
Oh.
That's the thing we want to look at. Negative.
And then cosine
Sine
of
theta.
theta.
And that's cosine negative theta is
Cosine.
just regular old cosine theta, which is just negative sine theta over cosine theta. And what's sine theta over cosine theta?
Tan.
So it's
Oh.
negative.
So it's negative tan theta.
So it's odd.
So it's an odd function. Tan of negative theta is equal to, is equal to negative tan positive theta. And of course it works in opposite order too, because a negative of a negative is a positive, and so da 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 blah blah blah, blah, right? And so, okay, so from here, we could get all the other ones too. We're not going to do that, but obviously if cosine has this property, so does secant. If sine has this property, obviously so does cosecant. If tan has this property, so does cotan, right? We're not going to do that, but maybe you want to. It would be a good exercise to just prove that. It's simple, real simple, but it's the same kind of thing here. Just say, tan of stuff equals this stuff over that stuff. And what we're trying to figure out is this an even or odd thing? And, well, I'll plug that in, plug that in, plug that in, and then just go from there, right? Okay, any questions on this? So you'll have to do some identities with that. And there's, a bunch of charts and stuff in your book giving you all this information. They're pretty good. It's real good. Okay, I'm gonna get rid of this, and we're gonna talk about the last stuff. Well, so like I said, you're gonna have identities where you're gonna have to use these facts and all the others for tangent and all the other ones. And then the last kind of stuff. So for numbers 9 through 16, or I guess 9 through 15 for you guys, it's worded weird, okay? They give you, so I'll just cut through all the BS in the book. They give you a T. They give you a T and want you to find. They give a T and they want you to find sine T, cosine T, etc. Okay? Everybody get that? Like, it's worded so weird. I want to cut through and just say, okay, this is what they're looking for. You're going to get, so for instance, number 14. And I think each one has like an A and a B. Number 14b, it just gives you this. So what they want, that's your T. They want you to find sine of that, cosine of that, and all the above. Now, how did we define sine and cosine? Just now.
The coordinates on the unit circle.
Right, so let's draw the unit circle. let's just do that. That might help, okay? Now, in what quadrant, and this goes back to quiz 1. It's why I wanted you to do this. Where is 3 pi over 4? And of course, from now on, we will always be measuring from the positive x-axis. So,
It's in the first quadrant.
it's in the first quadrant?
No.
No.
Oh wait, oh.
Right, and we can count by pi's over 4. Here's
Oh, is that?
1 pi over 4, 2 pi's over 4, 3 pi over 4, right there. Okay? And so, okay, in other words, this is what they've given you. 3 pi over 4. They want you to find, I'm going to go ahead and do it like this, sine 3 pi over 4. Cosine, 3 pi over 4. Tan, 3 pi over 4. Also, cotan 3 pi over 4. I would like to see you write all this stuff out as well. Just while we're learning this, it'll be really good for you to see what you're doing, okay? And so please write out all of these guys. Cosecant 3 pi over 4. Okay? So, now this is where those triangles come into play. If this guy's 3 pi over 4, what does this guy have to be right there if I measure just that right there?
1 quarter pi.
Yeah, or as I call it, pi over 4.
Pi over 4.
I think most people do say a quarter pi. I say whatever it is over whatever, that's just how I say it. But yeah, a quarter pi or pi over 4, which means that you know this triangle, don't you? What triangle is that?
45, 40.
Yeah, and so what would they, now there's two ways we could do this. We could just shrink it, right?
But with the radius is 1, so it's 1 root 2.
So 1 root 2, and so then how could we shrink it?
So multiply. Oh wait,
Wait,
divide
no,
by root 2.
Yeah.
If we divide everybody through by root 2, then we have this length right there is 1 over root 2. This length right there is 1 over root 2, making the coordinates what?
1 over root, negative 1 over root
Negative 1 over root 2, and then is the y positive or negative?
positive.
It's positive, so a positive 1
And that's
over
the
root
sine and
2.
cosine.
And there's your sine and cosine, right? Like, so sine of 3 pi over 4 is what?
Negative 1, no. I mean, no. 1 over root 2.
Positive 1 over root 2. Cosine is?
Negative 1 over root
Making tangent what?
1 over root 2 over negative 1 over root 2.
Which is?
Is it just negative 2? Oh, wait, no. Negative 1.
Negative 1. Negative 1, right? Because you have the sine, which is the 1 over root 2, over negative of the exact same thing. Whatever number that happens to be. If that was a 75 over a 75, it would always be negative 1, right? Right?
Yeah.
Okay. Cool. So then what's cotan?
Negative 1.
Still negative 1. What's this?
Negative root 2.
Negative root 2. And that's what? Root 2. Just plain old root 2. Now, another way, and this is what I was trying to say last time. You could shrink it, and you have your points, and everybody's happy. Or you could look at the reference angle, and you don't have to deal with this, because watch what happens. So here's your reference theta, or in this case, I guess it's your reference t that you're talking about. You know that this is 1 square root of 2. And so if I said, well, okay, what's, and I know that this is that's a negative number down here. That's a negative 1 over root 2, so I can call that negative. And now I can just do it the way that we've been doing it with opposites and hypotenuse, yeah, all that stuff. And I'd say, well then sine is opposite over hypotenuse, so sine would be 1 over root 2, which lo and behold is the same thing as that. I'd say cosine is adjacent over root 2, so it would be negative 1 over root 2 and all that. So there's a few different ways you could deal with this. You pick the way you like the best, get the right answer, and you should be good to go, right? So, does everybody get that?
Yeah.
You see why I really wanted to drill where all these things are on the unit circle? Like if you know that 5 pi over 6 is right here, your life is so much easier. Just knowing in which quadrant everything is. And then, when you know that, well, okay, I know that if that's pi over 6, which if that's 5 pi over 6, the great thing about the radian measures is that the reference angles are always just over whatever it is.
Yeah.
So if it's like 11 pi over 6, that right there is a pi over 6. And so you're dealing with this triangle, which I, wanted you guys to work with, right? So now you can see why this is going to be like, if you just have these pictures in your head and you know where all the angles are, the rest of this class will be a million times easier than if you were every single time going, wait, what? Hold up. But if it's 3 pi over 4. Good night, you know. So, okay, can I erase all this stuff?
Yes.
Everybody got this? All right, let's do another one. Oh, that was number 12A. Number 12A, same setup. They give you a t, and it's 5 pi over 2. Okay. Again, I'm thinking unit circle might help. Although it's pi over 2, so that's not too hard. Where does that one end up? Let's think about this.
It's the same
Oh,
as
it's
just
just
pi over 2.
It's the same as just pi over 2. And this, so there's a couple ways that we could think about this. You could just count by pi's over 2. Whatever this is over, you could just say, okay, well, just keep going. Just 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. And I get to where that is, which I find out is the exact same thing as this. Okay, and we're happy. Or you could, you know, like, you could say, well, I know that this is 2 pi. And since I'm over 2, I guess that would be 2 pi, 4 pi, 6 pi, and all the above. And I could say, well, 4 pi over 2 is 2 pi. Then one more would be, 5 pi over 2. However you want to do it, right? So a bunch of different ways of doing it. So like if I had, I don't know, 1,001 pi over 2. I would not count 1 pi over 2, 2 pi over 2, 3 pi over 2. I would just say, well, wait a minute. 1,000 pi over 2 is 500 pi, which is an even number, so it's over here.
And then 1 more.
Then one more would bring me right to there, right? Yeah, and so on and so forth. However, ooh, this would be an interesting one. Let's do this. What about 15 pi over 2? Well, 14 pi over 2 would be 7 pi, right?
And one more.
Yeah, but 7 pi, is that over here or is that over there?
That's.
Yeah, this would be pi, this would be 3 pi, this would be 5 pi, this would be 7 pi, which is the same thing as 14 pi over 2. So then this would be 15 pi over 2. Careful with those. That's especially when you get a whole number, you're like, I'm over here, I'm good, you know. Careful, it's even and odds, they're different. Okay, so you tell me. Now, that's where 5 pi over 2 lives. So, what's sine 5 pi over 2? Sine is the which value, the x or the y?
X.
The x. And no, wait, sine does not do
It's
x.
the y.
It's the y. It's the height. Okay, the sine, and I don't think about it as x and y. I think about it as the height. And so it's the height. What is that height right there?
1.
It's 1. You're on the unit circle, right? In case we weren't being 100%
That's
clear.
a lot easier than how I did it.
I know, and that's why, in the email I wrote you, I was like, "Don't worry, we're gonna clear all this up." It's simply the height. There's nothing new about that. Like, that's a 1. That's a -1. Well, so in the x direction, that's a 1. In the x direction, that's a -1. In the y direction, that's a 1. In the y direction, that's a -1. Okay. So what does that mean for cosine? What's cosine 5 pi over 2?
It's 1. Wait, negative. Wait.
What x value is that?
Oh, 0.
It's
So
0.
Oh, wait. Oh, yeah.
This is x. We're thinking about that as x. We're thinking about that as y. It's right here, and so we just look down and say, oh, it's 0.
Yeah.
Now, and you can see, like before, it was like, well, you can't have a triangle like that because if you can, you have these two. Yeah, because we're not doing that anymore.
With two
Forget
right.
about triangles right now. I mean, use them if they're helpful, but if they're not, that's not even part of our definition.
Triangle.
Right?
with two
Our
right.
definition is just points on the unit circle. And so sine is 1, cosine is 0, because this point right here is 0, 1, right?
Yeah.
There you go. Therefore, tangent is what?
Undefined.
Oh! It's what?
You.
Undefined, right? Undefined. And I think your book has a U when it
Then it
gets
gets
there.
confusing with the units.
And so That's undefined because division by 0, at least in this class, is undefined. Okay? So, okay, what's cotan?
1 over undefined, which is just...
No, it's not 1 over undefined.
It's 0 over 1.
Uh-huh, and what's 0 over 1?
0.
Boom! Yeah, tricky. That's why I wanted to do this one. Because you think, well, if that's undefined, its reciprocal has to be undefined. The only reason it was undefined is because it came out to be that, which is undefined. But its reciprocal, that's totally defined. You could do that. There's a perfectly good definition for that, and it's 0. So careful. So, what does that make secant?
Undefined.
That one's undefined.
And
And
sine's
then
the same.
cosecant is what?
Also,
No, it's
no, yeah.
1
Oh,
over...
that one, yeah, I got that.
Okay? All right. That's your homework. Now, we're going to move on. Okay? Any questions before we do so? All right. Okay. Now, I just said this is how we're going to define sine and cosine and all that. And that is going to be our official definition for what sine and cosine, and therefore all the other functions are in this class. But there's a better way to think about these guys. And this is how we're going to do it. Okay? Let's say I have a point. And we're going to start off where t equals 0. Okay? T being the measure of the angle, right, measured in standard position. We're going to start right here, where t is equal to 0. And we're going to imagine that we have a point here on this unit circle, and it's just going to move around like this as we increase t, right? And you could think about t, this is suggestive, as time. As time goes, it moves, say, 1 radian per second, or whatever. And so after 2 pi seconds, it's back to where it starts. After another 2 pi seconds, it comes right back to where it starts, right? And so whatever, right? And what we're going to do is we're going to have a wall. We're going to have a wall right there. And we're going to take a big old flashlight. And we are going to shine a light onto the wall and project the height of the point onto the wall. So that when time is equal to 0, the height is right here. And now as time goes on, as t increases, this point is going to go up. Does this sound familiar? And it's going to hit 1, because that height is 1, right? And then as the point continues on, it's going to come back down. And then it's going to come back down to here, down to, what's the height here?
Negative 1.
-1. And so it's going to bounce down to -1. And then as time keeps rolling on, it's going to come back until after 2 pi seconds, it's back to where it started. But we're not going to stop there. We're going to keep going. And so this point on the wall is just going to keep going up and down forever. It's almost like the ball we started off with at the beginning of the lecture goes straight up, comes straight down, but now it's going to go back up and back down and back up and back down. And we could imagine what that's going to do if we were to graph this phenomenon. Same kind of thing. It's not that this thing is moving off in this direction. But we're just going to keep a record of how high it is. As a matter of fact, and let's go ahead and think about this height as y.
That's what. Oh, I see.
And so what's going to happen is when I start my clock, I'm here at t equals 0. Okay, so when t equals 0, my height is 0. And then as t increases, right? And so here's my t. That point starts to come up until it reaches finally when t gets up to, what value of t brings me up to the top? What value of t? The output, the height is 1. What value of t would that be?
Pi over 2.
Pi over 2. So after pi over 2 seconds, we're at there. And then, right, once we're there, it starts to come back down. And it keeps coming back down until we're here. And how many seconds was that?
Pi.
That was pi seconds. Then what happens? it continues on and it drops below here, and we're just keeping track, right? Until it finally comes down to -1 at what time?
2 pi. Wait.
It's down here.
2 pi over 3.
How about pi over 3? I
Oh,
mean, how
yeah.
about 3 pi over 2?
3 pi over 2.
Man! Ah! And so then, okay, so we're just, right now we're just doing one cycle, right?
Yeah.
It goes, as it does this, it comes up, goes back down, comes back down. Now it starts to go back up, and it hits here after how many seconds?
2 pi.
2 pi. Does it stop?
Keep going.
No, it keeps going because like again, we've defined this for all real numbers. And so it's just going to, as a matter of fact, it's going to be an exact copy of this here and then here. And
That's why when you
here.
put this in sine x onto Desmos, that's what you get.
That is what you get, and it goes on forever. This is called a periodic function, meaning that there is a period after which, and I think about it as time, after which a certain amount of time, the exact same thing repeats over and over and over again. Now, the height was what in terms of our trig functions?
Sine.
No, yeah, sine.
Sine. So this is sine t. We have just graphed sine t, one full period of sine t. If we had gone in the opposite direction,
That'd be the end. Wait, no.
if we had gone in the opposite direction, well, let's just see. After it would, instead of going up, it would have gone down, and it would come to a minimum right here at -1 after how long?
Well, just still pi over 2.
Yeah.
And we're going to think about that.
Negative
It's
pi.
now negative pi over 2, because now we're measuring in terms of negatives, right? If we had gone in the opposite direction, we would be going -1 radian, or -1 degree, minus 45 degrees, or whatever, right? So this would be minus pi over 2, where it hits its minimum. It comes back up after how long? Where are we when it comes back up to
Negative
0?
pi.
Negative pi comes back up and hits a max where?
Negative 3 pi over 4.
Negative 3 pi over what?
2.
2.
Oops.
And then back down after
Negative 2 pi.
negative 2 pi. And you'll notice this is the exact same thing as this.
Yeah.
Right? Like really, it's as though you just took this picture and shifted it, which should be exactly what you get, since this is a circle and it just keeps coming back, and back, and back, right? Does that make sense?
Yeah.
Right? Turns out this, and yeah, this is what an odd function looks like, right? You go over this much, you go up that much. Well, if you go in the opposite direction by the same amount, you go down by the same amount. Or you go in the opposite direction. You come over this much, you go down that much. Well, if you go in the opposite direction, you go in the opposite direction. This is like the canonical example of, we're about to do that. Canonical example of an odd function. Now cosine, we want to graph x as a function of t. This is x, and so what I'm going to do, this is going to look a little weird, but then we'll make everything not so weird in just a second. I'm going to shine a light down this time. There's my flashlight. I'm going to shine the light down and project it onto a wall right here. And now we see, when I do that, what's the x value right there?
1.
1, right? Because we're on the unit circle. So there's the 1. And so this is what I'm going to do. Same thing. I'm just going to think about, okay, time's going this way, right? And in just a second, just so that our brains don't break, I will be drawing this thing in the correct orientation. But I want to use the same circle to get the gist of what's going on first. Does that make sense?
Yeah.
Why I'm doing it this way, right? Because sine is the height, and cosine is how far you're going in this direction, right? So let's graph this direction. It starts at 1 when t is 0. Then what happens? Does it get bigger or does it get smaller as t increases?
It gets smaller.
Right, because look at what the light's doing. The light's projecting down. This point starts off here, and then as t starts to go, it gets closer and closer to 0 until you're up to here, and it's actually at 0. Does that make sense, what just happened there? Does that look right?
Yeah.
Right? As t goes on, that point that's right here moves. As far as x is concerned, it's getting smaller. It's just keeps getting smaller and getting smaller until how many seconds have gone by?
Pi over 2.
Pi over 2 seconds. Then it continues to go down. It continues decreasing as we go beyond, and it keeps getting farther and farther down until it stops. And what's the x value right there?
Pi.
The x value, yeah, I know.
Oh.
So the actual, this axis, that's -1 right there. And that happens after how many seconds?
Oh, pi.
After pi seconds, that's what happens. Then, as t keeps cranking along, right, it starts to move back this way. And so it comes back until we get to here, and it's being projected right there, right? And that happens after how many seconds?
3 pi over 2.
3 pi over 2. And then it continues back to where it started, like that, back up to 1 after how many seconds?
2 pi.
And so if we redraw this,
So it's just like shifted a little. Wait.
yeah, as a matter of fact it is, and we're going to see that soon enough. But this one, so this one started up here at +1, it went down, hit -1, came back up. It got to there after pi over 2 seconds, it got to its minimum at pi seconds, it came back to 0 at 3 pi over 2 seconds, and it finally returned to where it started after 2 pi seconds. The height is 1. The smallest height is -1. And you see what we're doing here, right? This is the x value, the value of the x coordinate as t goes along, right? It starts at 1 because the x value starts at 1. And it decreases until it gets down to -1. As you can see, it decreases until it gets down to -1. And you're right, these are just shifted by pi over 2. If you took this function and you shifted it by pi over 2 in this direction,
So, wait,
you get the same thing.
sine minus 2 pi over, pi over 2 equals, I mean, wait,
Sine t, how do we shift something to the right? Or how do we shift this to the left? Do we add or subtract? So then sine t minus pi over 2 is cosine t. You're right. And we'll get there. We'll get there. And so what we've just graphed is cosine t. Cosine is even or odd? Was it even or odd? What? It's the other one. If it's not odd, it's... Well, actually, no, remember, a function can be neither even nor odd.
Oh, right.
But in this case, it is even, which means it's symmetric about here. So I don't even need to go back and trace things backwards. I could just say, and I could have done this
so what
with
was the odd one? It was tangent.
Yeah.
tangent and sine were both odd.
Oh.
Cosine, now, it's just a reflection. And if it's just a reflection, then what point is this?
Negative pi.
Negative pi over 2. What point is that?
Negative pi.
Negative pi. What point is that?
Negative 3 pi over 2.
Negative 3 pi over 2. And finally, it comes back to where it starts. Negative 2 pi. This is how you want to think about sine and cosine. Trust me. Like, yes, we defined it to be points on a circle. But now we're going to think about them as functions or graphs of functions, right? And this soon you will be quizzed. You will have a quiz. We have to draw more pictures, and these pictures will be this right here. We'll do it again before I give you the quiz, so don't worry about getting all this down. But I'll say 2 full periods of sine and cosine. This would be 2. Well, I didn't finish it up here, but 2 full periods is, you know, until it repeats again, right? So you can start here, and it goes down, and oh, now it's repeating. Okay, so that's 1 period, and it's good to go in the opposite direction too, so we'll get a full period this way.
Yeah.
Ditto right here, right? I didn't actually finish this guy off. He should come back down at negative 2 pi. But that is how we're going to think about these things. Okay? Let me check our time and see. Now, okay, perfect. So now you don't have any homework on this stuff yet, but pretty much everything we do in this class hereafter will involve these pictures. And next time we'll see what all the other trig functions look like based off of these. We'll be able to get tangent, we'll be able to get secant and cosecant from these 2 pictures right here. Now, since we're done, but I just want to see, is there any questions about what any of this means and how I got it? Right? Okay, we're just keeping track of, because the way we define sine and cosine now is simply its height or left and right, you know, its coordinates on the unit circle. And if you just track the movements of x as you move around, this is what you get. If you track the movements of y as it moves around, this is what you get. This one's easier. This is the easier one to see because it goes in the direction that you think of. Height up and down is this way. This, it's a little bit different because you have to do this weird stuff, but this is what it means. It's the same relationship here. We're just orienting it differently. Since, I mean, we're not really in a huge rush, you want to do that question, that problem?
Yeah.
Yeah, let's do that. Okay. So, all right.
Oh, number 41.
Yeah, could you read that to me? It said like simplify or something, right? It was just, yeah. It was like 2 plus tan or something.
2 minus tan over 2 cosecant minus secant.
Yeah, just like 5 times this.
Well, did you see when I tried to be like, this is what you do? Oh wait, no, that doesn't work. And I was like, well, this is just. Oh wait, I messed that up. So I'm sorry, 2 cosecant, then what?
Minus secant.
Minus secant theta. Okay. The first thing I do is something like this, because now it's not an identity. It doesn't give you equals some such and such, right? It's just like you're supposed to. I guess technically what you're doing is like in the back of the book, or like in reality what you're doing is you're looking in the back of the book and you're going, I need to turn this thing into that thing. So it is kind of like that. And when I see something this ugly, the first thing I do, regardless of what kind of question this is I'm going to say, you know what, why don't I just go ahead and turn this into sines and cosines. That's going to be my first thing. So since that's 2 times cosecant, and cosecant is 1 over sine, I'm just going to write that as 2 over sine. 1 over what?
Cosine.
Cosine. Now here's the thing. Here's another thing. This has nothing to do with trig. This is just because I've had algebra beat into my head so many times. But when I see something like this, I have fractions inside of fractions. I think it might be easy, maybe or maybe not. It might be easier if I kill all of these little fractions.
Yes.
And so, what do I multiply the top and the bottom by that's going to kill every single one of those fractions?
Sine times
Cosine
cosine.
times.
Okay, so I'm going to go sine times cosine, both on the top and on the bottom.
Yeah.
Okay, now let's go ahead and I'm going to distribute that in, and I get both of those jump over and hit the 2, giving me 2 sine cosine. And this is where I messed up when I was doing it on your. These jump over, something cancels.
Sine squared.
Yeah, sine squared. And when I was doing it on yours, I just wrote sine. And then I was like, what did I do wrong? Whatever, you get full points. So it's sine squared because the sine times the sine, right? Okay, now on the bottom, these jump over and what's left over here?
2 cosine.
Just 2 cosine
Oh, and then
Minus sine.
minus 1 old sine. Now thinking back to just regular old algebra, is there anything we could factor from anywhere?
2.
you can factor sine from the top.
I could factor
Oh, yeah.
sine from the top, because you could think about this as like a 2xy minus x squared, say, well, I guess I could get an x out of there. And do I want to do that? I don't know, but I could see right here that if I do, the thing that's going to be left over is that's going to look, that'll be nice, right? So that's what I'm going to do. I'm going to say, okay, let's factor out one sine out of the top. So there's one sine theta that pops out. I'm going to leave the bottom alone. 2 cosine theta minus sine theta. And then once I pull that out, that guy's gone, leaving me a 2 cosine theta minus 1
No, sine theta.
sine theta.
Oh, 1 second. Yeah. I thought-
Yeah, right? Yeah, check me on that, right? I just pulled out one sine from each one of those. Left me a 2 cosine there. There should be one sine left over there. So then that divided by that is 1
nice.
giving me sine theta. Yeah, that's a tricky one.
That's easier than it should.
Right, and like, and I think I saw what you were doing. You're trying to use some, thing. I think you're trying to use secant and tangent. We know they're related somehow. Maybe if I use them, it'll make life easier. And when you first start that, that's often where your brain goes. Like you go, wait, hold up. I just learned this thing about tangent and secant. They're related, and I think it's like 1 plus tan squared equals secant squared, and so maybe I could do some kind of, I almost always, if you put everything, now this doesn't always do it, because sometimes, yes, this is absolutely the way to go. But oftentimes, my first step is this. I just say, you know what, let's just put all of these in terms of sines and cosines, and maybe that makes your life easier. Maybe you get to this point and you go, that made things much worse. I don't know what to do now. Then maybe go into the other stuff. But at first, my first step is almost always turn into sines and cosines. Do I see something obvious? Well, I see a bunch of this. I know what to do when I have denominators and denominators. And did it make my life easier? Oh, it turns out that's it. I'm done. Right? But sometimes you take a few steps and you go, okay, that was the wrong direction. I have no idea what I'm doing now. Maybe now I'll go into this type of stuff and try to relate some things. Maybe it'll help, maybe it won't, but that's the idea. Cool?
Yep.
Awesome. All right, guys. I will see you guys Thursday.